Okay, so what we have here is our control center for the spin rig. On the left-hand side, we have the basic machine controls that allow us to monitor voltage, current, speed, and so on for the system, as well as control inputs such as motor torque or speed of the system. So in this instance, we've got a manual control here to alter the current coming into the motor. So we're altering the torque of the motor to hit our target speeds. They're the main things you need to consider on this side of it. And we have in the middle our live monitor, so we're watching in real time what's happening on the test rig. And then I'll hand it over to Ben.
On this side you can see, as I've shown previously, the acquisition system here. We're currently armed, so we're seeing live data coming through. I've created a virtual channel in here, which is the difference between the two laser vibrometer signals for the velocity, angular velocity, so we instantaneously get a delta omega. The green channel here, which is essentially the vibration across the coupling that we've shown. We've deliberately damaged the coupling in this scenario here. We're about to begin a run-up test. We use this power supply here to set the voltage across the coils on the eddy current brake. So we're currently setting this to 6 volts, which will be about an intermediate load. And I'm going to arm the system. We're going to create this run-up, taking RPM increments between 200 and 1800 on the input side of the system. So I'm going to press play, and then Paul's going to gradually manually increase the RPM, and you'll see these peaks in the spectrum increase, and when we hit a resonant frequency, those peaks might increase significantly during the course of the run-up. Away we go. Thank you, Paul. Here you can see the RPM gradually increasing, and the acquisitions as we cut through this 100 RPM increments, 6 acquisitions, 7, 8. So these are individual FFTs at different RPMs, and we'll ultimately generate a waterfall. Here you can see this peak slowly progressing through the spectrum, and when we hit a resonance it gets slightly higher, and then it drops down again. That's the end of the run-up now. So we have 17 FFTs. Paul will slowly drop the speed down on the machine. I'll say that I want to save the data. We can then disarm the system so we're no longer ready to do a measurement, and I can save the project here so we don't lose any of our data. Go back into the navigator screen over here, and I can browse then within this navigator for the most recent run-up, which is this run-to data here. I've defined some online processing, and if I expand through here, you can see the vibration channels. I've got 8 different vibration related channels, including my delta omega, which was the channel that I generated, the virtual channel that I created, which is a subtraction between those two measurements. This is a measurement from before that's currently being displayed. If I create a new picture here, I can choose to put a new waterfall in here, and so we can have an instantaneous look at these data. So that's a new waterfall, for example, that it's an alternative to a colour map. So I can take this measurement data and drag these into this area here. I can move over here and change the format from amplitude to logarithmic scale, so you can see these individual waterfalls at 100 RPM increments. More intuitive maybe is to show that effectively from above with a colour map display, and if I choose in this case to take the auto power spectrum from the Z direction of the accelerometer, which is in the direction of the shaft, now you can see some activity within this, what's referred to sometimes as a candle diagram. And so if I change the axis on the x-axis to 256 Hertz, you can quite nicely now see here, if I put a single cursor on the x direction, we believe that there's a resonance around about 31 or 32 Hertz. So if I move that cursor to 32 Hertz and put a harmonic cursor on here that shows 20 cursors at integer multiples of the meshing frequency, so it's a 2.5 to 1 gear ratio, and so half order for the output shaft is at 1.25 times the RPM tacho, and so you can see there the 1.25 order cursor intersects with this natural frequency at 32.5 Hertz, and we have at that point a large peak in the frequency spectrum, which is where the resonance is being excited by the driven frequency.